Now again, as we have discussed, there are two failures chances of there for the central pin. One is shear failure and second one is if we consider the central pin as a beam which is subjected to equal and opposite forces of the single eye and double eye, this pin will try to bend with try to bend because of the two equal and opposite forces. Means what? This double eye will try to pull this pin at this place and this single eye will try to pull this pin in the another end. So because of that, this central pin will be subjected to for example, this is the central portion of single eye. There will be a rectangular distribution of the forces. This analysis is similar to the analysis of the quarter joint, except only, and in this case, uh, there will be a triangular distribution of the forces where the point of contact takes place with the double eye, right? This is central line, right? So this analysis, for understanding this, we have to find out center of gravity of this point. Center of gravity, at the point of center of gravity, the applied force will be F by 2. At the point of center of gravity of this half portion, the applied force is F by 2, right? So this is the distribution of the forces at the point of contact with single eye and at the point of contact with the double eye, right? So there is a triangular distribution of the forces and here there is a rectangular distribution of forces. Now we have to find out bending failure. Means there will be a bending stress. This pin will try to bend from the center, right? And what is the cross section of the pin? The cross section of the pin is circular cross section. So with respect to axis YY and with respect to axis XX, it is subjected to equal distance, that is diameter of pin by 2 half portion. So what is the extreme fiber? Y, that will be diameter by 2. So sigma b, again we remember that in case of quarter joint, m upon y into y, which is called as flexural formula that we have studied in strength of material. Now what is the bending moment takes place in the failure of knuckle joint? Bending moment is also always force into perpendicular distance. But where the maximum bending moment takes place? The maximum bending moment will takes place at the portion shown in the diagram. So maximum bending moment will takes place between this f by 2 and between this f by 2. This portion will having a maximum bending moment. So either above the center line or below the center line, we have to do the analysis similar to the quarter joint. So we have to find out the maximum bending moment taking between this section. So bending moment is always force into perpendicular distance. So force into perpendicular distance, force into perpendicular distance up to center and force into perpendicular distance up to center, right? So what will be the moment that we have to find out? Before that, what is the moment of inertia I? As it is a circular cross section, I will be equal to pi by 64 into diameter of pin raised to 4, right? And y is equal to, as we have discussed, it is a circular cross section. The distance of extreme fiber from any one of the axis is d by 2, hence y is equal to d by 2. Now bending moment m will be equal to, if we take f by 2, what is the distance from here? This distance, this is equal to t2. This distance is equal to t2, so f by 2, this much distance will be equal to t2 by 3 plus, so f by 2 into this much distance, t2 by 3, and this distance is equal to this distance, this much distance is equal to plus t1 by 4, right? Plus f by 2 into this distance, so f by 2 multiply by, we have to find out this distance. This force is at the center of gravity from the center line, top portion of the center line. So this, as this total distance is equal to t1, this total distance is equal to t1, hence this distance is t1 by 2 and this much distance is t1 by 4. Hence f by 2 into t1 by 4, right? So sorry, we have made mistake here. We'll erase that. This is minus. So now why minus that? I'll repeat it again for you. My mistake is there. So maximum bending moment is taking place between the uh, point of contact that is in between this f by 2 line of action of this f by 2 to line of action of this f by 2, that is distance between these two. To find out that distance, we have first found it out f by 2 multiply by perpendicular distance up to center. So f by 2 multiply by this distance was t2 by 3 plus this much distance was, so t2 by 3 from here, and this much distance was t1 by 2, t1 by 2, sorry, this distance is t1 by 2 minus f by 2 into t1 by 4, so minus f by 2 into t1 by 4, so this distance was t1 by 4. Understand? So what, this is maximum bending moment. If we put this maximum bending moment here, we have found out I is pi by 64 into d raised to 4 and y is equal to d by 2. So all these parameters are in terms of uh, d, and we have to write down the equation of t1 and t2. So what are the equations of t1 and t2? So t2 and t1, t1, that is distance of the single eye end, t1 will be taken equal to 1.25 times of d. Now from where it came? It came from the empirical relation or past experience, and t2 is taken as 0.75 times of d to calculate the diameter of the pin, right? So if you put this value, the design of the quarter joint will become safer by empirical relation. So to calculate the diameter of the pin, we'll first initially assume t1 is equal to 1.25 times of d and t2 is equal to 0.75 times of, sorry, capital D is here, that is diameter of this rod, right, which we have initially found it out. So here we have found it out this. So by doing this analysis, we will get again the diameter of the pin from this bending stress analysis by doing this particular thing. So diameter of the pin from shear failure and diameter of the pin from bending failure, whichever value is having maximum value, we select for the further design, right? So whenever there comes two moves of failure and we get the same dimension body, that moves of failure, we will have to select the maximum value, so that in case of the failure, uh, in case of the chances of failure, we select the maximum value of the dimension, right? So for P, there are two chances of failure, bending and shear. In both the failure equation, stress equation, we get the diameter of the pin, and from the two diameters of the pin, we select maximum. The next one, tensile failure of the single eye. Now we are going to start now design of the single eye. Now this single eye will be subjected to tensile load. Due to that tensile load, this portion of the central eye from the center, there is a chance of tensile failure when it is subjected to assembly. Complete assembly is subjected to tensile load. There is a chance of tensile failure of the rod. That means this single eye will break from the central portion and will separate from the complete assembly of single eye. So this diagram represents the failure of the single eye. So what will be the cross section of that? So if you see from this side, the cross section will look like this, right? So this portion will be cleared away or filled by tensile mode, right? This is the center line. So what is the diameter of that pin? What is the diameter of that rod? So this single eye will be filled by that mode. This complete dimension is d1. This is equal to diameter of the pin d, and this dimension is equal to d0, right? So from this diagram, what is the failure? Tensile stress. What is the applied force? Either P or F. What is the area? Cross-sectional area. What is the cross-section? Now in this case, cross-section will be equal to d0 into d1. So d0 minus d into d1. So d0 minus d into d1. So from this equation, d was known, d1 thickness was we have put d1 we have put as 1.25 times of d, and d was known. D is maximum D from shear or bending failure. Only unknown was D0. We can find out that D0. Understand? Now if P is known, sigma T is calculated from SYT and factor of safety. We can easily find out this D0. Right? This is tensile failure of a single eye. Next one is crushing or bearing pressure of single eye or P. Right? Now in case of the knuckle joint, when it is subjected to tensile load, the central pin will try to crush the single eye surface, or single eye surface will try to crush the pin or compress the pin. For example, the area where single eye has hold the pin will try to crush due to the movement of the knuckle eye joint, and it will try to crush it or compress it. But in this case, we are not going to call this as compressive stress. This is called as crushing stress, because the whole surface is getting compressed. Not a single point is subjected to compression. So this kind of stress is either called as crushing or bearing. Now why I have put two failures are there, crushing also and bearing also. This is oblique. Why that I have done it like that? Because if the knuckle joint is subjected to tensile load, there will be a crushing if there is no relative motion between pin and single and double eye. If there is no relative motion between the joint, then the stress will be called as crushing. And if there is a relative motion, because in the some of the component of knuckle joint there is no relative motion between the remaining two components and the pin. But in some cases, like example of tractor and trolley arrangement, there is a relative motion between the pin and that single eye and double eye. In that case, it will be called as bearing stress or bearing pressure, and if no relative motion, called as crushing stress. So we are going to write it by same way. Phenomena is same, formula is same, but only what will be called as whether bearing pressure or crushing stress. That depends on whether there is a relative motion between central pin and the remaining two components in within which the crushing or compression takes place. So it is equal to applied force divided by now which area? The area will be projected area. So remember, crushing and bearing pressure is always applied force divided by projected area, right? So what is the projected area in this case? So projected area in this case will be if I project this rectangle, right? And now if this is the surface, if I project it, which is under crushing, so this portion, if I project it, it will look like as this surface will look like as a rectangle, having how much is the dimension? This dimension is thickness T1 and this dimension is D. So this is D and T1. So projected area is equal to D and T1. Now again, D is known, T1 is also known. So from this equation, you can put diameter D here and you can calculate T1 here. Or what we, as we have T1 is directly inserted 1.25 times of D, you can put both value of D and T1 and you can calculate crushing stress. Now what we have to do with that? Crushing stress or bearing pressure is always SYC upon factor of safety. SYC depends on the material of the single eye, because we are calculating crushing of the single eye. So SYC is always 1.25 to 1.3 times of SYT. From where it came from the thumb relation or empirical relation. So SYC is 1.2 to 1.3 times of SYT, where SYT is yield strength in tension. If we put this value SYT 1.25 times SYT upon factor of safety, we will get either crushing or bearing pressure, and applied force will be given in the problem. Now D is also known, T1 is also known. If we put all this value and if we calculate sigma CR from this equation, if we calculate sigma CR and by using this equation SYC upon factor of safety, if we calculate again a sigma CR, this is calculated sigma CR from the formula, this formula, and sigma CR allowable from the equation of strength. So for the safety of this two dimension, this allowable sigma CR has to be greater than that of the calculated sigma CR. From where it came? It came from, let me erase this, I will discuss with you the concept from where it came, the safety of the design. Now as both the dimensions were known to us and we are only calculating the allowable stress, and calculated stress, we are comparing them. So after comparison we must know from where it came. So we know that this is called as stress strain diagram from the basic of strength of material. This point is called as ultimate tensile strength. This point is called as yield strength in tension. Now for the safety of the design, what I have said, allowable stress has to be greater than that of the calculated stress. Now in this case, calculated stress is from this equation, allowable from this equation. Allowable we have calculated on the basis of SYT. That means to have the safety of the design, allowable stress has to be greater than that of the calculated stress. If calculated stress goes beyond allowable stress, from the stress strain diagram we know that the component will be failed after reaching this breaking point. So from the for the ductile material, the criteria of failure is SYT. Hence, to avoid the failure, allowable at this point has to be greater than that of sigma calculated, and for if this equation satisfies, the dimension of D and T1 will be safer, which we have calculated earlier. So understand, so here we only check the safety of the design as though the dimensions were not